This evening's presentation is entitled Insulting the World's Oceans. UVic is a national and international leader in the study of oceans. Our ocean-related research spans the campus in many ways, from ocean-climate interactions, the subject tonight, to coastal resource management and wave and tidal energy, to name just a few areas. Tonight, we are truly fortunate to have two of UVic's most established and recognized researchers giving us their thoughts on oceans. It's one of the great jobs of being the AVP of research that you get outside your faculty and you learn about the research going across campus, and nothing could be more nicer than to introduce two well-established and well-recognized colleagues. I'm going to do both introductions so that I don't break the flow of the presentation, and I'm sure you can figure out who is who when they do their presentations. Dr. Verena Tunnicliffe is the Canada Research Chair in Deep Oceans. She is a professor in both biology and in earth and ocean sciences and director of the Venus Network. As an enthusiast of marine biology, Verena has worked on mudflats, coral reefs, fjords, seamounts, and in deep sea environments. Her work focuses on animal adaptations to the challenges of the physical, chemical, and geological world. Dr. Tom Pedersen is the director of the Pacific Institute for Climate Solutions and a professor in the School of Earth and Ocean Sciences. Tom began his professional career as an exploration geologist searching for ore deposit in Canada's north. Curiosity about the Earth, and particularly the ocean, propelled him back to graduate school 2 years later and a PhD in marine geochemistry. He joined the University of Victoria in 2002 and has held positions as director of the School of Earth and Ocean Sciences and as Dean of Science. For many years, his key area of research has been paleoceanography. Paleoceanography, in plain language, which I should have used, the history of the oceans. And these days, he has added to that the policy realm, and particularly what human society needs to consider in shaping our own future in the face of global warming. So it is my great pleasure to introduce our speakers. After the presentation, there will be some time for questions and discussion. Tom?
Well, good evening, ladies and gentlemen. Thank you for coming out on a rather breezy night here in Victoria. It's a great pleasure to see this wonderful turnout tonight. We've got a great week lined up here at the University of Victoria in terms of the Idea Fest celebration. Tonight, Verena and I are going to discuss with facing in direct response to the issue of climate change and global warming, which is, in fact, the issue of our times. So we've titled this Insulting the Ocean, Impacts of Climate Change on the Seas. And of course, by using the phrase insulting the ocean, we are referring to what the human species is doing to our seas. I'm going to begin by setting the stage, and I'm going to give you a little bit of a more global overview, and then Verena is going to come along and give you some wonderfully exciting, detailed analysis of what's happening in our coastal waters here along the coast of British Columbia. Everyone in this room is probably familiar with this iconic image. This is the Keeling curve. Charles David Keeling started measuring the concentration of carbon dioxide with very, very high precision in March 1958 at Mauna Loa in Hawaii. And at that time, I was just an infant, or almost an infant. The concentration was about 310 parts per million when I was born. As of this morning, it's 393.09. Now that's an almost 40% change in the lifetime of one baby boomer. And that's an important consideration. I really want that to register tonight. This rate of change is extraordinary. To the best of our geological knowledge, Mother Nature has never imposed a rate of change on an atmospheric constituent like carbon dioxide at this rate ever before in the history of the planet. We are changing things at an unprecedented speed now. And that's very important for us to keep that in mind. And so we're sitting up there at 393 parts per million. And that, of course, is helping to drive global warming. This is elementary physics of the atmosphere. We know this very well. There's no argument about it. You might find it on the pages of the National Post, but you can discount those because they're not telling you the truth. I want to show you an animation in support of what I just said, my contention there, that was produced around the end of January by NASA. And this is a beautiful piece of work that I'm sure a big team labored over for some time. What you're going to see is 127 years of thermometer measurements averaged over the surface of the Earth relative to the 3 decades of 1951 to 1980. And you can see that in 26 seconds. So we're going to start in 1884. We're going to go through time now. Coming in the early 1900s, it's still cool, relatively speaking. As we get into the 20s and 30s, it gets a little warmer. The yellow and red colors get warmer. It cools off a bit in the 40s, 50s, and 60s because of the post-Second World War industrial expansion and aerosol input to the atmosphere. As we get into the 70s, 80s, 90s, and the 2000s, look what happened. And there we are today. Now, this is not science fiction. This is not a model output. This is thermometer measurements. Thousands and thousands and thousands of thermometer measurements that have been compiled to yield this result. It's getting warm. And it's particularly getting warm in the high northern latitudes. And Canada, of course, is right in the epicenter of that. That warming of global air temperature is reflected by warming in the ocean. And we can see that very clearly in terms of ocean heat content, in this case in the upper 700 meters. These data come from NOAA. Sidney Levitas has compiled this data set. In this case, the last half century, 1955 up to 2008. And you can see that we've been accumulating heat in the upper ocean quite progressively, particularly since that warming that really kicked off starting in 1970. Now, when you warm the upper ocean, you reduce its density. So you can think of kind of pouring oil on top of water. And that lower density water that is subject to this warming is harder to mix down into the ocean interior. This becomes really important because oxygen in the atmosphere gets into the ocean interior in part by downward mixing. And we're starting to inhibit that now in the world's oceans. So that leads us into the big questions that Verena and I want to ask tonight. Are we losing oxygen from our waters in the sea, and particularly in the upper part of the water column in the open ocean or in our coastal waters? If we are losing it, where are we doing it? Where is it being lost? And why is it being lost? What is the intersection with human activities? And particularly, I want to talk a little bit tonight about energy policy. And then we're going to go on to discuss what Robin Brown at the Institute of Ocean Sciences just up the road in Sydney calls the evil twin of global warming. It's a wonderful phrase, evil twin. I call it the hidden sister. In one of my publications, Robin's a little more accurate with evil twin. And that is the issue of acidification. Carbon dioxide dissolved into seawater produces carbonic acid with negative implications which are very serious, as Verena in particular is going to show you later. So let me start now with oxygen in the Pacific. What you're looking at there is a cross-section of the Pacific, and if you can imagine taking a great big cleaver and just smacking it down vertically right here from Alaska right down to Antarctica, cleave the ocean in half, and then look at the cut face. And that's what we're looking at here, is the cut face. From the surface right down to about 5 kilometers depth. And you can see it looks a little bit kind of like a clubhouse sandwich on its side, with nice colors at the top, particularly reds, that are indicating high oxygen concentrations. This is now dissolved oxygen in the Pacific. And you can see that the warmer colors up here are high oxygen. The cold colors, purples and blues, are low oxygen. So we have high oxygen at the surface, and that's, of course, reflective of mixing largely by wind and currents that is stirring oxygen into the upper couple of hundred meters. But we can also see high oxygen here around Antarctica. That's a circumpolar current that's whipping around Antarctica at the bottom of the Earth, well-mixed water, and it gets very cold at the surface. When it gets cold, it gains density, just exactly the opposite of what warming does. So that water that gains density here sinks, and you can see what it does. It carries oxygen down into the deep sea as it flows north. It follows that kind of pathway. But as it's flowing north, it's also losing oxygen progressively because there's no new sources of oxygen at the seafloor. So oxygen is progressively being consumed. And you might ask, why is that happening? Well, it's because there's a constant rain of organic matter down into the ocean interior from the little plankton, phytoplankton in this case, plants that are growing up here in the sediment surface waters, sinking down into the seafloor and consuming oxygen. That oxygen is being consumed through decomposition process. But that doesn't explain this part of the clubhouse sandwich, this purple zone. Look at the concentrations of oxygen in this water here in the North Pacific. They're very close to zero. We call that the oxygen minimum zone for obvious reasons. It has low oxygen in it. And that water is the oldest water in the ocean. And when we say oldest, oceanographers say old water, that means water that's been away from the atmosphere for a long time. This particular water, not too far off our coast here, out here in the Pacific, this particular water mass is as much as 1,200 years old, in the sense of when it last was in contact with the atmosphere. It's not being mixed very readily. There's no new source of oxygen into it. It's kind of a stagnant lens of water that sits there across the North Pacific. Very old and very low oxygen concentration in it. Now you can imagine what's going to happen to that water mass in the future. If we further restrict the ability of the atmosphere to supply oxygen down into the ocean interior because we've inhibited mixing by warming in surface layers, that oxygen concentration is going to go down. This water has an oxygen concentration that's so low that fish cannot live in it. They'll suffocate if they swim into that water. Verena is going to show you some data later on in support of that. So what is happening in the ocean then? Well, there was a nice paper published by Lothar Strama in 2008. He's based in Denmark. And I'm going to just show you a little piece of that. He compiled all of the oxygen measurements that he could get in the world data sets and binned them into pieces of the ocean. So here's the North Subtropical Atlantic and the Eastern Equatorial Pacific from 1960 to 2007. And this is scaled now in terms of pressure, but you can think of that as depth, the top 1,000 meters or so. And look what happens to that oxygen minimum zone. Through time, as we come forward in time toward the 2000s, you can see that the oxygen minimum is expanding. And it's also happening in the equatorial Pacific, a very slight expansion. If you project that into the future, what we're looking at is a loss of about 10% of saturation per century. And you might think that's slow, but in geological terms, it's very fast. And it's very worrying for those areas of the ocean that are already oxygen deprived. And we're further adding to that deprivation now by consuming more oxygen. The explanation for this is in part, at least, due to the imposing of a lid on the surface of the ocean of lower density water. What about closer to home? There's a famous oceanographic site off our coast here, off west of the northern end of Vancouver Island, called Station P, or Ocean Station Papa. Used to be the site of a Canadian weather ship for many, many years. And many measurements of ocean characteristics were collected there, including temperature and salinity and oxygen and so on. These data, compiled by Frank Whitney at our Institute of Ocean Sciences, run from 1956 to 2006, so a half a century of data. The top panel shows temperature over that time at 3 water depths, 140 meters, 370 meters, and then one in between here at 170. And you can see that over time, although it's a very noisy set of data because the ocean, of course, is not static, even in the shallower water, the temperature is getting progressively rising, slowly rising, as a consequence of the warming, the data you saw earlier, the accumulation of heat in the sea. The noise is somewhat damped at greater depths, but nevertheless the trend is the same in an upward direction. And here's what oxygen is doing. It's going down. Between 140 meters and 370 meters at each site it's going down. In this case, if you extrapolate further, we're looking at something greater than 10% loss of saturation per century. The worrying trend. The worrying trend. Let's move now into coastal waters. The story gets gloomier, by the way. It gets a lot gloomier here, but we don't want you to leave the room tonight with a sense of doom and gloom and go and jump off a bridge or anything like that. What this means is it's a challenge for humanity to turn around the way we do things. And that's, I think, one of the messages that we'd like to deliver tonight. But we're now going to go into coastal waters and look at a new type of, or relatively recently discovered phenomenon, which we call dead zones. Over the last 110 years, perhaps, there's been a steady growth, apparently, in the number of zones that have very low oxygen water on the coastal margins of the world's continents. We call these dead zones because fish that succumb to the low oxygen concentration in them do die. And Robert Diaz at the University of Virginia compiled as much data as he could get his hands on from the early 1900s up to very recently, and he estimated the number of dead zones around the continental margins of the world, and he averaged them per decade. Now the data back here are rather poor. The data up here are very good. The implication is that there's been a very strong rise in the number of these low oxygen water masses that are sitting on the continental shelves or the upper continental slopes around the margins of the world's oceans. And in fact, if you look at the use of nitrogen fertilizer in agriculture globally, this graph corresponds with the rate of growth of nitrogen fertilizer use. The implication is that we're putting additional nutrients into our coastal waters through our river systems, largely from runoff from farmers' fields and the like, and that's supporting the growth of plankton, algae, which then die and sink and consume oxygen from the subsurface water mass. One of the best studied of such water masses is here in the northern Gulf of Mexico. This little white label here says the toxic zone, and it is located off the mouth of the Mississippi, which of course drains much of the continental interior here of the United States. And it's the best, perhaps the best studied hypoxic zone on the planet. In July of 2009, that zone of low oxygen water sat over about 8,000 square kilometers. In 2007, it's 15,000 square kilometers. And a very large mass of water in the subsurface now, between maybe 100 meters and 200 meters water depth, where the oxygen concentration gets perilously close, for example here, perilously close to zero. This is toxic water to animals. A crab, for example, on the bottom that gets caught in this water mass that it moves up on the shelf dies. What's the cause of it? Well, first of all, there are large plankton blooms now in this region every summertime or late spring, and the cause of that, in fact, is nutrient additions coming down the Mississippi River. Those nutrients are being derived from the intensive agricultural activity here in the heartland of the United States, and particularly in this zone that's marked in red here. This is the yield in kilograms per square kilometer per year of nitrogen going into the Mississippi water courses, primarily from agriculture, although there's also contribution from sewage and so on. And that's being carried right down into the Gulf of Mexico, supports the phytoplankton bloom, the plankton grow, bloom, die, sink, decompose, and presto, you have a dead zone. And on top of all of that, the Gulf of Mexico surface waters have been getting warmer year by year, and it's more difficult to mix them down and thus get oxygen down into the subsurface. If you look at the amount of nitrogen that's coming down the Mississippi River, and this has now been monitored very carefully since the late 1960s, you can see that it rose through the 70s. It was pretty static or even decreasing up to about 2005 or so. And in the last several years, it's picked up again. In the spring of 2011, it was about 22% above the long-term average. So this is a very difficult situation the United States finds itself in, because this is an environmental insult for the sea, which is primarily related to the need for food. But there's another factor that's really intruded into this in the last several years, and that's energy. And these are the few comments I want to make about energy policy. In the Bill Clinton years, when Bill Clinton was president, he started to encourage the production of ethanol as a substitute for gasoline in internal combustion engines. It was a very noble objective. The idea was to lessen the dependence on imported oil, largely from the Middle East. George W. Bush in 2005 proclaimed the Energy Policy Act. That was in July of 2005. And he set a renewable fuel standard in that act that required 28 billion liters of ethanol to be produced in the United States annually by this year. That got reinforced in 2007 by a different act, the Energy Independence and Security Act, that set a target of 57 billion liters of ethanol annually from corn. From corn. Now, corn uses a lot of starch and sugar, which is readily convertible to ethanol. It's actually a pretty good substrate for ethanol production. But corn is also a grass. And a grass requires a lot of energy, a lot of nitrogen in order to grow effectively. And so the effect of these policies, which of course included a fairly significant subsidy of 45 cents a liter for each liter of ethanol produced, led to a corn rush in the United States. Not a gold rush in this case, but a corn rush. And so land that was lying fallow suddenly was planted with corn. Land in Nebraska that was too dry to grow corn suddenly got planted with corn. New wells were sunk, and groundwater was pumped out to irrigate the corn. Massive jump in the production of corn, and a diversion of some fraction of that corn into the ethanol stream. 37% of American corn production now goes directly into ethanol production instead of into the food supply. 37%. Now this was a noble objective. We want energy independence. We want energy security. Ethanol is not a bad fuel if you can produce it from something that doesn't have other harmful effects. But in this case, it had a very serious distorting effect on the renewable fuels market, and particularly on the world price of corn. That first act was proclaimed at the end of July of 2005, and the second one in December of 2007. And I've marked those here on this chart showing the world price of corn running from 96 up to last October. And you can see what the impact was. When you take, in fact, the United States is the world's largest exporter of corn. But if you take a big piece of that production and divert it away from the food stream, this is the effect it has. And so there were food riots in places like Kenya and in Mexico. You might remember the tortilla riots in Mexico in the late 2000s. A direct side effect of energy policy in the United States. Independent of the hypoxic zone, it was also being exacerbated by the nitrogen added to supply all of this corn. So sometimes our policies don't do the right thing. My suspicion is that when the 2005 and 2007 acts were proclaimed, or as they were being developed, the legislation was being developed, my suspicion is there was no oceanographer at the table. I also suspect that there may not have been a food security analyst at the table. There should have been. Let me go on to our last point that we're going to be discussing this evening, and that's acidification of the ocean. This is the evil twin now. And I want to make one key point before I show you an animation, and that is that in the ocean we have a lot of dissolved carbonate in the form of carbonate ions, and those ions are combined by organisms with calcium to produce their homes, to build their houses or build their shells. And they build them typically from limestone, or what we would know in the chemical world as calcium carbonate. So you can think of carbonate ions dissolved in the sea as building bricks. And if you take an ion out of here, you're essentially taking a building brick away. Well, when you dissolve carbon dioxide into seawater, it forms carbonic acid. And carbonic acid immediately reacts with the carbonate ion and removes it. Makes it unavailable to organisms. So by adding carbon dioxide to the atmosphere, and thus into the sea, what we're in a sense doing is we're taking building bricks away from those organisms that need it to produce their homes or their skeletons or their shells. A little while ago, about 2 weeks ago or so, the Pacific Institute for Climate Solutions released a series of YouTubes, which we call Climate Insights Bite Size. I'm going to show you one of those now. This is about 4 minutes long, and it's our attempt to explain acidification of the ocean in lay language, and I hope that this will.
The addition of CO2 to the atmosphere by human activities is a primary contributor to the greenhouse effect, but it is also causing another serious threat to our planet, the acidification of our oceans. Join us as we explore this threat and its implications. Carbonate is a key building block for calcium carbonate, the solid materials secreted by organisms like corals, clams, and oysters, and even some plankton, in order to make their skeletons or shells. When carbon dioxide dissolves in the sea, it reacts with water molecules to form carbonic acid. Carbonic acid, in turn, reacts and consumes dissolved carbonate in the ocean. The penetration of human-induced carbon dioxide into the sea is now progressively consuming carbonate ion. And as carbonate continues to be stripped from the upper waters of the ocean, corals and other shelled organisms will find it more difficult to grow. The result could be large-scale loss of coral reefs from parts of the ocean within the next 2 centuries. Scientists have been measuring the serious change in ocean chemistry for over 2 decades, and concern is growing rapidly. These data were collected at an oceanographic station called Station Aloha, just north of Hawaii. This site has been extensively monitored since about 1988 by an international team of scientists. The bottom axis represents time running from 1988 to 2009. The top graph shows carbon dioxide concentrations, while the bottom graph shows the acid content of the water, in this case made by measuring a parameter called pH, where lower pH values indicate higher acid content. Several observations can be derived from this set of data. First, the red line in the upper graph shows the atmospheric carbon dioxide concentration, with parts per million on the vertical axis. The blue line shows the dissolved carbon dioxide content in the surface seawater. It is more variable and reflects changes in ocean circulation, changes in the intensity of photosynthesis being carried out by plants in the sea, and variability in temperature. The trend is unmistakable. The dissolved CO2 concentration in the surface ocean is rising as atmospheric CO2 content increases. And as chemistry would predict, and the declining pH indicates, the surface seawater is progressively becoming more acidic, in step with the increasing dissolved carbon dioxide concentration. Why is this so important? Simply stated, a declining carbonate content, that is, a declining number of available building blocks, will make it increasingly difficult for corals and the other organisms to build their shells, their houses, and thus to survive. Coral reef environments have remarkable biodiversity and yield about half of the marine protein consumed by humans. So the threat posed by acidification has serious implications for our future food supply and the overall biological health of the sea. Ongoing ocean acidification is the hidden sister of global warming and a major issue. As we continue to add CO2 to the atmosphere, the dissolved CO2 concentration in the surface ocean will also rise, causing increasing ocean acidification and threatening the very survival of tropical reefs and many shellfish. The projected large-scale loss of coral reefs from parts of the ocean within the next 2 centuries has serious implications for biodiversity in the sea and our future marine protein supply. And that should be cause for serious concern for you and me.
That's one of 10 YouTube videos that are released to the web on the internet, so you can find them on our website or on YouTube if you wish. We're going to move on now and invite Verena to come to the podium. She's going to take you on a wonderful journey here in the British Columbia coastal waters.
So I'm going to start back with the oxygen, and I'm going to go and we'll revisit the acidification at the end. So let's talk a little bit about oxygen and what it means to the animals. This curve here shows us what happens when we go up to Mount Everest. And think of where we live right now and the amount of our world that has what we call a well-habitable environment. As you go up into the Himalayas, you got to put the oxygen mask on. But look what happens when you go into the ocean and take that same amount of oxygen and look at what happens going down. So very little of our ocean is habitable in terms of that normal oxygen amount in the upper waters, because there is that oxygen minimum zone that Tom mentioned as we go down, and then we pick up the oxygen again near the bottom. So this is in the North Pacific. Okay? So we use the words normoxia, that's the normal oxygen, hypoxia. This is where some organisms can cope, but as you go into acute hypoxia and head to anoxia, that's when the habitation decreases. So you'll find in lots of different numbers are used for this, and I'll just keep using the word hypoxia here to show where we're going. So as we look into an ocean area that is diminishing in the amount of available oxygen, there are numerous biological consequences. And if we just think about what happens to us as we begin to lose oxygen, this particular graph came from a teaching video on anesthesiology, worrying about the amount of oxygen in your patient. So here, with the amount of saturation, you've got normal brain function, and you go through half the amount, then your muscle paralysis into unconsciousness. That's what these organisms in the ocean also begin to suffer. From that, we see mortality, the loss of habitable areas, and because the amount of habitable area diminishes, you're going to have animals moving into the regions of other animals. So your species are now going to start competing. Meanwhile, you've got metabolic and physiological effects that are going to change your reproductive capability and your growth rates. And these animals are now functioning differently in the environment. All of these organisms play a major role in the ecosystem, and nutrient cycling is just one of them. We also anticipate a major loss in many of our commercial fisheries. For example, the Japanese are currently seeing in the waters off their coast a switch to more abundance of jellyfish. And this is particularly true in areas where there is low oxygen occurring. And that is because jellyfish are relatively better at low oxygen. So here we have mackerel and the moon jelly. And this is an experiment that was done in the lab. We've got increasing amounts of oxygen, and then we look at the ability of the fish and the jellyfish to catch their prey. And their prey are little baby fish larvae. And as oxygen increases, we find that the mackerel do much better at catching prey. But when oxygen decreases, the jellyfish do better, and increasingly better. And that's because they are not much affected by the lowered oxygen, but the prey are, so the larvae aren't swimming nearly as well. So this means low oxygen means it's a bad thing for the mackerel, but it happens to also be a bad thing for possibly the fish larvae that could then increase the populations later, because the fish larvae are also being affected here. A few years ago off the coast of Oregon, there was a massive kill of fish and crabs and shellfish. And that was because of a dead zone that developed off Oregon in both years. This was directly a response to a change in the normal weather pattern that we see in the North Pacific. All our weather comes in the middle of the Pacific. And the behavior of what's called the Aleutian low, or the Aleutian pressure cell, shifted a little bit in these years. And as a result, the winds continued from the north much longer than they normally do. And with that increased wind from the north, longer and longer duration, the relative outflow of what happens as the Earth rotates is that the surface of the water moves offshore with winds from the north. So we see this displacement of water offshore and the upwelling of water underneath to come upwards. That's a normal process, but because it kept going on and on, get more and more water upwelling, that's our low oxygen water that's coming upwards. That caused severe hypoxia as shallow as 50 meters in depth. As a result, you saw lots of dead fish, lots of crabs washing up in the beach, and I couldn't find a good picture. This is a snap from a little movie I had. These are all piled up dead Dungeness crab at 45 meters in depth. The whole bottom was absolutely littered with them for a very large area off the coast of Oregon. Let's see. Okay. What I'd like to show you now is coming right home here, and some work that a number of scientists are doing using the Venus Observatory System in Saanich Inlet. We have an array out in the middle of the Strait of Georgia, but we also have an array here in Saanich Inlet. And the reason people wanted this there is Saanich Inlet is a naturally low oxygen basin, very high productivity in the springtime, and that productivity sinks down. The bacteria use up the organic matter, and they use up the oxygen, and therefore low oxygen occurs with very little refreshing water coming in at depth. So we have an observatory system on the seafloor, and one of our instruments is a camera. So our scientists wanted to look at what is the effect of hypoxia on the bottom communities. So the camera was deployed down at 105 meters in depth, and every 3 days for a year, the camera took pictures of the bottom, covering about 5 square meters of area. And so this is from 2009-2010. And these pictures are taken throughout the year, going through. And you can see there's a big variability here, going from this white fuzzy stuff on the seafloor to areas with lots of these crabby-looking things. There's actually quite a few fish in a couple of those pictures as well. So obviously big changes are happening over the years. So this is the oxygen at this particular location over the year. So we see lots of variability, and we see a period of very low oxygen, and that's extremely low oxygen. When I talked about hypoxia, hypoxia starts at this value here, and then you go into acute hypoxia, and then into anoxia. So we have very, very low oxygen conditions, and then it begins to rise a little later in the year, and then tapers off again. Again, I stress these are natural, but it gives us the opportunity to look at how the animals respond. We find, interestingly, there's a lot of critters down there. There are 3 major species in quite high abundance. We have the little squat lobster here, Munida quadrispina. We have a flatfish, and it's called the slender sole. And then on the bottom are all these tiny little shrimp. These guys are only about 1 centimeter long. They're very, very small. But they're incredibly abundant at extremely low oxygen. So obviously, animals can cope. But what we find is none of the species that support our commercial fisheries are down there. And over collecting information over a number of years, if we look at the oxygen concentrations, and there is hypoxia right there, that 1.4, down to acute hypoxia. So these yellow triangles here are all the squat lobsters. And it's only until you get up to about 1.5 that the spot prawns come in, and then the crabs come in up here with a couple of lone guys venturing down here. So the commercial species are requiring the higher oxygen conditions. So the little slender sole I mentioned that's down in the low oxygen, that's not a commercial species. The commercial species, the English sole, for example, only occurs at higher oxygen. The octopus only occur at higher oxygen. These are high energy animals needing much higher oxygen. So there can be life in hypoxia, and some of these animals that we look at are really well adapted. These little squat lobsters, when they go down into the hypoxic conditions, they actually grow extra gills so they can pull that rare oxygen out of the water. So they have bigger gill volume. The flatfish go really dormant, and they don't move unless they really have to catch prey. And they really ventilate. The gills are just going like mad, so they're pushing a lot of water through. One of the other sides of anoxia is the production of hydrogen sulfide. That occurs in zero oxygen. We get sulfide coming out of the sediment. That's also a poison, so there's another input of a stressor into the system. And this white woolly stuff is a rather intriguing microbe, a filamentous bacterium that uses sulfur in the sediment as an energy source. So when you see the white woolly stuff growing, that means there's sulfide in the sediment and very low oxygen overlying. Tom showed you information of over the years what's happening off our coast in terms of lowering oxygen. It is happening in our waters right here as well. One of the ambitions for the observatory is to be able to document that long-term change. And if we look at the Institute of Ocean Sciences records over particularly the last 50 years, and these are the Venus data in here added to it, what we find is that we're losing oxygen at those times of higher oxygen. So we're getting lots of times of low oxygen, but the breathing room that happens at certain parts of the year is occurring less and less. This is a particular slice of water right down where I showed you the images. So we're just looking at that little slice. And this becomes quite a concern when you think about, okay, we've got those animals that are adapted to the low oxygen, but certain kinds of the year, the other animals can expand into it if the oxygen is there, if it begins to come back in. And this is saying no longer is that oxygen coming in very easily. So just on the wider picture, looking at our coast, this is also data from Frank Whitney's work where he's looking now much more closely at our coast, and we're seeing oxygen at 200 meters depth. He's seeing rates of decline everywhere. He's looking at long-term records from fisheries and oceans, and we're seeing long-term diminishment of oxygen in our waters. So what happens as we begin to diminish that amount of oxygen? Again, if we look at the depth profile going down to 2,000 meters, here's that oxygen minimum zone that Tom mentioned. This is our hypoxic zone. Most of our commercial species are in water over that minimum zone. So if that begins to expand, that means the habitable area for the commercial species is going to decrease. So the estimate is that the non-hypoxic habitat is going to start disappearing over the next few decades. Those animals are going to be squished up, and they're going to start competing with each other. There are animals, see here, these guys do go down into the oxygen, the top of the oxygen minimum zone. Those animals are also going to come up a little bit shallower as well. So, looking at a little bit more detail on what the fish habitat is, here I've now put this graph on its side. So this is deep water, this is shallow water. Here's our hypoxia down in here. And look at all these species now that are just up in that habitable zone, and the ones that are near the hypoxic zone as that boundary begins to move upwards. What the catch records show from 10 years of data, where are the fishermen catching the fish now? Now they're beginning to find that the catch is moving shallower and shallower. So it really is happening. It's moving up. The guys that are shown in red here are species that in which the catch has gone markedly down in the last 10 years. So are these guys doomed? Are we doomed? As Tom has mentioned, we start thinking about the nutrient input into the ocean, And for places like the Baltic Sea, for the Gulf of Mexico, we really can do something about that. If you turn off the source of the nutrients, you can turn off the effects. And that has been shown in the Black Sea as well. When the Russians stopped putting a whole bunch of nutrients into the Black Sea, it recovered. That can be done. The problem that we have on our coast is that our dead zones are not caused by nutrient input. Our dead zone, our diminishing oxygen is caused by that stabilizing temperature in the ocean that Tom mentioned and changing weather patterns. The oxygen that's going into the ocean that will affect us 50 years from now has just happened. So there's a huge amount of momentum in our system. The problem is if we don't start doing something about it now with climate change action, it's going to keep going for a very, very long time. So the momentum is already in the system. It's hard to stop what's going to happen on our coast in a very brief period. So, compounded with that is the acidification problem. And this is a rather intriguing one scientifically because it was, for the most part, not predicted by the scientists. We really thought the capacity of the oceans to deal with our carbon dioxide was enough. And what Tom mentioned is the rate of change is what's taken both the science and the ocean by surprise. The biological effects of ocean acidification, you saw the movie talking about the problems with skeletons, particularly Tom's movie focused on the coral reefs. I just want to bring it home to British Columbia here. The ocean absorbs about 25% of all the carbon dioxide we put into the atmosphere. If we had to do that ourselves and take it out and do something with sequestering that carbon dioxide, it would cost us somewhere between $1 and $4 billion a year. So the ocean actually is doing us quite a good service. The problem is the deposition of those calcium carbonate skeletons. And not only the skeleton problems, if you also have a more acidic conditions, it begins to cause physiological problems in the cells, the animal trying to buffer its capacity within its own tissues, and you end up with, well, you know what it's like when you're running, you got too much CO2, you end up with cramps in your legs. That's acid changes in your body. And so your body now has got physiological responses. We have a large number of animals, little plants rather, sorry, let me start that again. We have both plants and animals in the ocean water which serve as major food resources in these size calcium carbonate skeletons. So these are the little sea butterflies that have very delicate skeletons, and the coccolithophores are two examples. This is a coccolithophore in normal water, and this is one that has been raised in a slightly lower pH conditions, and the rings are now distorted. There's little bits of erosion. That's the problem with these. Their skeletons are getting weaker. Okay, so this set of maps shows us what's happening as we move from current conditions, 2020 to 2050. The areas that are red on the map are increasing acid waters, and the areas that are blue are somewhat less problematic for acidic conditions. And I think the point that I just want to make to you is just look where we live. That's the big blotch of red here and here, and the other big blotch of red is down in the Antarctic. But we are going to get hit with it first on our coast. So these predictions are actually quite easy to make, relatively easy to predict where the water patterns are going to. So it's not really subject to a huge amount of scientific argument. So that's going to affect the ability to make shells. So this is an interesting piece of information. Here was a study that took the ship right through Tunnicliffe Strait and then down into Hood Canal. This was conducted by NOAA that will come into Canadian waters. So this is remember, do what Tom said, take a slice of the ocean, going down through the water column here, and the normal pH in ocean waters is around 8.2, 8 to 8.2. If you get numbers that are below about 8, we start to worry. And in 2008, look at that big slosh of red water that came in through the Strait of Juan de Fuca and eventually ended up down here in Hood Canal. That point right there is just in Harrow Strait, down to Pat's area. That water also went into Strait of Georgia, although we don't have the measurements. That's our source of water into Strait of Georgia. If we look at calculating what the ability of an animal is to be able to retain its shell, there's this number here called omega. And if you see a calculated omega value less than 1, it means the shell is going to dissolve. And here's the calculations here, and all of these numbers in here are below 1. That causes a major problem for shellfish, and particularly difficult for larvae. For the little tiny scallops and oysters that are trying to settle, they have a particular kind of calcium carbonate that's very, very fragile and susceptible to this problem. This was also the time that the scallop fishermen in Washington State began to notice a problem with the spat and the sets in the scallops. And one of the areas up in Qualicum Beach was also seeing a problem. So the water intake was down around 7.5. Now that is acidic water. So I just wanted to give you a really brief example of what it's like to live in a high CO2 world. I happen to be very fortunate in another part of my life. I do a lot of work on hydrothermal vents in the deep ocean. And I had a chance to go to the Mariana Volcanic Arc. So just whip to the other side of the ocean now. And there's Japan, and Guam is down here. And I'm just going to, these photographs are from a volcano called Ifuku Volcano. And Ifuku Volcano is an amazing place with its hot vents. It also has a huge amount of carbon dioxide rising out of the volcano. And it happens to be just at the particular depth where the state of the carbon dioxide that's coming out is liquid. It's not gas, it's liquid. There's these bubbles of liquid coming out and slowly rising up in the water and then dissolving as dissolved CO2. Right up above this is at about 1,500 meters depth. Right up above, there's the smokers, is a huge field of mussels. A massive number of mussels. So we have a high CO2 environment. How do these guys manage to do it? I'm not going to give you the entire story here, but what's particularly amazing is that these mussels are living in pH values that are amazingly low. Remember I said the water is normally 8. We worry if it gets below 8. These mussels are living it down to 5.3. So the message here is that life is amazing. The very fact that these guys can do this is absolutely astonishing. But for them to do it, and we did a comparison between these mussels and the same species living in a pH 8 environment. These guys are absolutely struggling. Their growth rates are half. The amount of shell they're putting down is absolutely minimal. And they have tremendous metabolic effects in the animal. They're absolutely struggling to live in this environment. And one of the reasons they can do it, it so happens that there are no crabs living on this seamount. They have no predator that can get into their shells. If they could, they would be wiped out. Those shells are amazingly fragile. We found it very difficult to work on them because they would just crack. If you put a light behind the shell, you can read through it. That's how thin the shells are. So that's what our animals, our oysters and our scallops and our shellfish around here are headed towards. And it's not just those animals. Tom movie told you about coral reefs. We also have deep corals in our waters. which will similarly have problems in precipitating their shells. So we're really quite unready for this in terms of how we're going to be dealing with it. This is, if you're interested, this is a very intriguing paper that was just published in Science just this past week. And it is a study on looking at the history of ocean acidification for 300 million years in the past. Basically, it's concluding that there's nothing like it in the history of this planet in terms of the rate. Started at the beginning talking about the rate of change in our ocean. And this is the same thing with the carbon dioxide. The rate of input into the ocean is like nothing that's ever happened. This particular image here basically says by the year 2094, anywhere in gray is really going to be in a world of hurt in terms of the amount that the ocean has acidified if we don't start doing something about it really soon. So what do? As I mentioned, this is a phenomenon that somewhat took the scientific world a little bit by surprise. The scientific community has mobilized really quite rapidly, and you look at the numbers of reports that have emerged in the last decade, it's quite phenomenal. There is a huge move to try and get action in terms of understanding, but also have some input into policy. There's very little resistance to the concept that CO2 injection into the ocean is causing acidification. The proof is really clear. It's that other part that we might be responsible for the CO2 in the atmosphere. That's the difficult part, as all of you might know. So this is what we're facing. The insults into the ocean from a triplet of conditions of change. We haven't really talked about the effects of changing temperature, but you're going to see migration and changes of organisms, plus the oxygen problem, plus the acidification problem. So what can we expect in the future? Depletion of oxygen in the open ocean, exacerbation of dead zones because we've got increased nitrogen inputs, and an extremely serious problem that relates to acidification. So what I just wanted to do to end here, I'm just going to pull the lights down a little bit, and I just want to show you, this is a trip through Saanich Inlet, or a trip through anoxia to normoxia. Turn that down. And this is just going to take a few minutes here. Right? So we're starting out at about 150 meters in depth in Saanich Inlet here. No animals, but you do see this white woolly stuff on the bottom. So we've got some plankton floating by with a few swimmers in the water, but nothing's living on the ocean, just this white bacterial mat. As we get up to about 120 to 110 meters in depth, look, here's our flatfish that I mentioned. This is an extraordinary little creature in terms of their capabilities of coping with the low oxygen, but still lots of mat. Now we're moving really fast up through 100 meters into 90 meters depth. Our squat lobsters flipping around here, and we're beginning to see more animals living on the bottom, and there's burrow marks, there's shells, there's sponges as we move shallower. Here we've moved into, wow, look at all the prawns on the bottom here. This is about 60 meters in depth, and anybody know what those white things are there? Pardon me? Sea whips. So they're kind of coral with a little calcium carbonate skeleton, and they're very like just deep sea whips actually. These are juvenile pollock. Now we've come up into full normal oxygen conditions with the anemones, and these guys can cope with some low oxygen, we move into the really active fish, like herring. The places they need to lay their eggs have to be full oxygen. The herring have returned into the Strait of Georgia as the fishing insults have diminished, and this is what we want to get moving towards in terms of a normal oxygen. We have the most amazing system, the ecosystem in the Strait of Georgia, in the Salish Sea area. It would be really nice that we can keep a very healthy looking ocean like that. Thank you very much for your attention. On.
Thank you both very much for the presentation. There's now time for questions and comments. And I would ask you, if you have a question or a comment, if you could move to one of the microphones so that you will be heard in the room and also on the webcast.
Gonna get anything from anybody? Don't be shy.
Verena, did your work say that the local habitat will be gone in 40 years?
No. It said the 40 years was that part of the habitat for habitable fish is going to be diminished by half. That is a prediction based on looking at the rate at which that low oxygen zone is coming up the continental shelf. Okay? So we're going, within 40 years, at this rate, you can expect to see that area fish, our current fish, coping.
What does DFO think about that, and what are our kids going to eat?
Thoughts on fisheries and oceans. I do know that they're concerned about it. Actually, a lot of this work does come from fisheries and oceans. Part of the messaging here is to look at how you manage. Some things we can't change fast. We can't change quickly that diminishment of the oxygen. What we can change is how we manage the extraction of the resources in response. But you want to make sure you still have sea populations left. So maybe that oxygen, low oxygen coming up, is going to squish it all up, making it easier to collect. So this is an iterative process where you're getting the information into the managers who are concerned about it, that do we understand well enough how you manage the fisheries. I don't know what it's going to do. My children are going to do too.
Daniel Pauly did advise us that we should learn to enjoy jellyfish.
There are places in the world you can buy dry jellyfish. They aren't very good, but
we can get used to it first. I'm wondering whether there's any discussion at all about geoengineering solutions here. These are, in some cases, not loose, fairly confined spaces. We know that there are a lot of problems in handling the CO2 emissions difficulties. We know there's going to be a lot of resistance to efforts to reduce the application of fertilizer in agriculture. Is there a nice, easy, painless solution in the geoengineering world?
Thank you, Rod. No, there's no nice, easy, painless solution. Solutions are complicated. Approaches are complex. There will be some pain in the sense of, pain is perhaps the wrong word. There's certainly going to be substantial adjustment to the way that we do things as a human society, and that's very large on the face of the planet. But I don't think pain is the right way to look at it. I think that what we should look at is, we should ask ourselves very vigorously, what are the structural adjustments that we need to be putting in place yesterday to forecast or at least to change the way the future is going to unfold for us. Right now, there's a huge inertia against that, as you know. It's largely political in nature, although I don't blame our politicians everyone else started from. And so we all have a role to play here in things the way we do things. And I do think that we need to impress upon our politicians, who are just a reflection of us, that we are very concerned and we should be taking action. Now, about to start there. So I haven't said that about geoengineering. We can certainly do things with respect to agricultural policy that significantly limit the amount of nitrogen that we are adding to coastal waters. This is already starting to happen in some places, and Verena rightly referred to the case of the Baltic Sea, where there were large inputs of nitrogen into the Baltic Sea in the past. They've cleaned those up now, the water quality is much improved, and oxygen has then returned to large swaths of similar black. So those things can be done. I actually have a slide from the computer that shows multiple green dots across the face of the earth where things have been cleaned up and things have been different. So it's not all bad. We can, for example, in the United States, there's an active program now to encourage farmers to adopt better techniques to put ammonium nitrate onto their soil. They actually waste ammonium nitrate. They put on far more than they need to get natural production. And there are varying techniques for me. There are multi-techniques that are big improvements. And the problem there is that the number of acres or hectares of corn that have been planted has skyrocketed. And they have programs in place to limit nitrogen application per hectare, but then you have many thousands more hectares not going to aggregate nitrogen content. So that's something that has to be addressed. Coming to the larger scale of geoengineering with respect to climate change in terms of greenhouse gas forcing, that's a real love game. We start to play with the atmosphere, we're going to get ourselves into deep trouble, I suspect. There needs to be an awful lot more research and much improved understanding on the implications of physical systems to try and limit the impact of infrared absorption by the sun before we even embark on such an idea. So, we don't want to go there yet. And in fact, the very best might be something we have to keep very firmly in our back pocket. It's an absolute last resort. And it should always be thought of as a last resort. We set the limit for them.
I have a question about plastics and the addition of plastic waste. I went to a lecture at UVic a couple weeks ago, and it was talking about what that is doing to marine ecosystems, specifically around the Southeast Asian Pacific coast. And I'm curious if you found quantities of that in your research in this area.
I've done quite a lot of deep sea diving in my life. I've never been anywhere that I haven't seen the influence of plastic or something. A lot of human input. The parts of, so you do have to do the research specifically for breakdown of plastic and the plastic products. It does have to be a focused program in that aspect, and there's no doubt that you're seeing a lot of uptake of plastics into organisms and into seafood. So we have certainly seen that. What are we worried about the most? That's something that we can fix. I mean, that is, I don't mean to say that it's not a problem we should worry about and focus on, but it's a fixable problem. We can change our plastic source, we can change our habits in disposal. And it's not a hurtful solution to us. Difficulty with the problem we're talking about is that the solution is hurtful to us, so that the ability to do that change is so much, such a larger wall to get over. I feel the plastic story is a really good example of how we can communicate well to the world. Here is the direct link of your action to the water bottle for this turtle that's choked to death. And it really is a good story about how humans can change the future. And I think we can use that as an example of it also solving that.
Hi, I just had a question about, in terms of low oxygen content in the ocean, talk about the effects on sea animals, but what about mammals, sea mammals, which actually obviously aren't affected by low oxygen directly, but I could see maybe they're affected by the food supply. In any other ways would they be affected by low oxygen?
come up with a quick yes on that because they're air-breathing organisms, and you're right to say it's the food supply. And that's the way they're going to be really most notably affected. It's possibly with well, the place that could be affecting them is this jellyfish-fish interaction, where all of a sudden there are places in the world where the ocean just turned into jellyfish. I mean, when the Black Sea went really, really low oxygen, it turned to jellyfish. So you can imagine that, the mammals that are trying to deal with their food supply, that is what's going to be affecting them. So I can see areas off Japan, if there's any whales left. You can see where the marine mammals would be affected. The most amazing thing I ever photographed under the camera in San Chile at 105 meters is a seal that came out and cut into the camera. So they will, so that part isn't bothering me, but it is if you hit that right.
I enjoyed your presentation very much. I know that currently on the eastern coast of Canada, there is some research being done in which they are extracting, not necessarily ethanol, but fuel that's similar to that from algae to produce fuel, and it's been successfully tested that it can run some combustion engines. I was wondering if anything like that was being done here on the west coast, and if that might be an area of interest, generating fuel instead of using cornfields.
Yes, there are schemes like that in the way on the west coast. I think that I'm not sure which specifics that I'm referring to on the east coast, but presumably extracting compound facilities diesel fuel. And there are attempts here to do some similar things. There's Enterprise University. They have a program underway there where they're storing use of certain types of algae as a fuel source. There's work here at the University of Victoria, in fact, to try and use bacterial approaches to produce hydrogen from different substrates using bacteria. So there are approaches underway where people are trying to produce various kinds of renewable energies from different reasons. The difficulty with them is volume, scaling up to the kind of scales we need, which is many, many billions of barrels equivalent. That's always going to be an issue, I think. And then cost is another issue. As long as fossil fuels are getting as cheap as they are today, we might not think that they're cheap because the price of gasoline is taking the bill up again. And in fact, they're pretty darn cheap. And as long as they remain so cheap, so it'll be harder for the renewable fuels to get into the range. Yes,
we're on the bucket, it's going to help.
Thank you so much for the presentation. It's wicked. I mean, you guys are totally at the top forefront of this investigation. My question is, this is something serious, and I'm sure everyone here agrees with that. And you guys are at the forefront of the investigation. So what happens when the policies behind do not match the results of your investigations? And how can you guys deal with that?
Well,
I do it perfectly. I do things like this. It help us.
I can't speak for Verena, but I just hold my hair up. Your question is an excellent one, and I think it's a question for everyone in this room to address. The challenge is not, it's no longer a technological challenge for humanity. We know what we need to do. We have the tools available to do what we need to do. What we're lacking collectively in almost every country, but certainly in North America and on both sides of the border, we're lacking the political will to do what needs to be done. And I think our biggest single challenge as individuals in our society is to get in place that, or put in place the political will. And until we start to speak constructively and loudly and make constant requests of our politicians to do better, not much is going to happen. Right now, the public in Canada is not making use of plants. They're more concerned about their jobs. We hear it all the time, jobs, jobs, jobs. And I'm afraid that's very short-term thinking. There will be no jobs at some point when climate change really takes root and shakes its planet. And we have to get beyond that very short-term thinking and start thinking in terms of multiple generations. Right now, we're not thinking. So it is a challenge. I get very frustrated. I must admit, I get very frustrated. I don't want any of you to leave tonight feeling frustrated. No, I want to be able to spring in your steps and say, you know what, we can change things. Let's get out there and start changing.
Yeah, it's one of our difficulties is that the Canada's governed by the Oceans Act. The Oceans Act is policed by Fisheries and Oceans, but our government is a landlocked city. And we are not sitting on an ocean, and that is a really tough message to get through. DC is near an ocean. The politicians do see the ocean. You do see much more of an understanding in Washington about ocean things than you do in Canada because Ottawa is what it is. And that's just got to be a constant routine. We've got to think about what our policies are and what are we doing.
So, I'm in a class called Coastal Communities, and we're learning a lot about, obviously, the coast and the island. And in terms of being on an island and an island community, how do you think that Victoria is vulnerable to change, the changing waters, the changing policies, and also how do you think we can manage the risk as being on an island rather than being on the mainland?
That's a challenging question for Victoria. Yeah. Well, the island has such a range of environments. It's actually one of the most fabulous places in the world. When you think of the inner strait, and then the southern, and then the fjords along the outside, and then what we're faced with on the northern area. As an island, we have to manage a whole range of coastal conditions. You probably well recognize that from the course you're taking. And so looking towards ocean traffic, if the Northern Gateway pipeline goes in, what are we dealing with the contingencies there that we have to think about? And the fishers and the coastal nations as well. So we're blessed. We're blessed with a tremendous diversity on this island, with the capability of us being able to understand something which almost nobody else in the country can because of where we're situated. So I think that becomes something that, in terms of the management becomes a difficult one in terms of the variety, but the ability to learn and to be able to teach is a tremendous one. And then we go all the way from the city to the totally remote locations. So looking at areas where understanding where the vulnerable habitats are, whether it's from tsunami, which we didn't talk about, or whether it's from the acidic waters, which tends to be probably in the inner strait area versus the oxygen waters, which may be a little bit more on some of the outer areas. And then some of the impacts for fishing and oil and gas on the northern island. I mean, all of these have to be carefully managed separately. I don't have a clean answer to your question, but if you think of the opportunity for people who are trained in coastal management, this is a really good one here.
One other factor we can add to that is that's of course sea level rise.
Oh, yeah.
Sea level is rising, and current estimates range quite widely. It depends what you want to factor into it, but the IPCC 2007 suggested that sea level by the end of the century globally would be somewhere between 18 and 59 centimeters or so. Most of the experts in the field now are saying that is way too conservative, and the IPCC assessment did not consider, in fact, they expressly ruled out rapid mass waste into Greenland or the West Antarctic ice sheet. If you include those now, based on recent estimates that have happened and measurements from satellite PET systems that we have, sea level rise is likely to be substantially higher than 58 centimeters by the end of the century. It might be even over a meter. So places like the Clough estuary are very, very sensitive to any rise in sea level. So the town of Belfast, for example, is very, very exposed to that. So those things have to be taken into account. What can we do about it? Well, we've got several decades. So one thing you consider is zone regulation. No longer allow building on tidal plains or coastal floodplains. We practice what's called managed retreat, where you progressively, as a building becomes aged or whatever, and you move away from it, and you move back from the shoreline. Because the shoreline's been falling in that retreat. So these sorts of things have to be factored in now. The British Columbia government is actually very active in considering this. They've got a big program with the Climate Action Secretary looking at that very issue. It includes extensive study on that environment. I think the report is available on the web, actually, if you haven't looked at it. These are the kind of things we have to do. But we have time. We just need to get action. We need to get moving.
I wanted to get back to the chemistry aspect of this a little bit. You mentioned that the oxygen depletion is a result of increased plankton production, and that's settling out. And I'm wondering if there, with that increased plankton production, is there corresponding oxygen increase in some areas? Or is that all going on in the atmosphere?
Well, that would be right on the very surface. So it's where the plankton are up there, and you're right, there is increased oxygen right at the surface, which tends to be an air sea. The problem is those dying bodies going down, and the bacteria then consuming oxygen to decompose them. But the oxygen problems are not caused just by increased production. It's caused partly by decreased injection of oxygen into those waters that are in the western Pacific, over towards Japan and up into the Sea of Okhotsk. That's partly where our oxygen is coming from. So normally, it's in the springtime when the ice melts in the Sea of Okhotsk. That melting ice takes the oxygen down, and that's what's feeding across the Pacific. And in Frank Whitney's work, what he's showing is that the rate of that oxygen injection from both the Sea of Okhotsk and from the mixing up from the subtropical near Japan, the amount of oxygen mixing in is decreasing because of, first of all, decreasing sea ice because of increased temperatures, and secondly, there's also more stratification, which doesn't allow movements. So that part of that equation, especially in the Pacific, is not related to increased phytoplankton production. Tom's talked about nitrogen fertilizer input. That's the part that's the oxygen from, the problems with phytoplankton. That's the part that we can control a little bit better. It's that western part of the Pacific that's happening today that's going to hit us, even though we stopped, that momentum's already in the system. So we've got a lot of decades of cleaning up to do. That's going to hit us 40 years.
No time to lose.
Who would like the final question?
We can give them a couple thank you.
Okay, so related to the last question about more oxygen on the surface, we've seen that jellyfish may benefit from hypoxia, lobster. I was just wondering if there are any commercial species, or is there any benefit for identifiable species at the surface that we might see increased oxygen at the surface?
I'd say change that to increase CO2 at the surface, because the other thing that plants need even though it's carbon dioxide, because they fixed carbon dioxide, right? So there are some algae that the increased CO2 going into the water actually increases their growth rate. And then they produce more oxygen, which is where Tom was going with his question. So there's a couple of scientific studies that say, well, there are certain species of algae that do better than increase CO2. And you'll see more production of those, the little bits of plankton, phytoplankton floating around in the ocean. That's great, but it causes the production that falls down and increases the oxygen problem as it decays. So it's not entirely a bad story that everything's going to hell in a handbasket. There are some things that will benefit from it. You know, change is tough. We can't predict exactly how that's going to go. So the answer to your question is yes, some things will always benefit. The one thing to take away from this is that life is amazing. We may kill ourselves off, but there's always going to be something that's going to do better than us in a changed world, and it will come out the other side. It just may not be the kind of world we wish it to be or that we are part of it.
Tom told me at the beginning, before we started, that this was a bad news presentation. There's one thing I know, you can't solve a problem until you understand it. So I think the good news is you both gave us a very good understanding of the issues and the challenges that we're facing. And maybe we do have to make our governments understand those better. So on behalf of everybody here, on behalf of the Idea Fest organizing team, thank you very much. So thank you for coming. I remind you again, tomorrow night, same place, same time, when we start at 7:30. There's a presentation on climate change and its effect on food security in British Columbia. Please turn in the feedback forms that are sitting on the table on the way out so we can have a better idea of how to organize next year. And if you haven't, pick up a brochure on the way out that has all the Idea Fest events that are going on this week. Thank you for coming.